Thank you, Dave. Good morning, everyone. My talk is about seismic sources, seismic receivers, how they can be improved, and the consequence of broadening the bandwidth. So the outline of the talk is following the introduction. Let's look at the receiver side, what we can do there. Share with you some experience, some data examples from around the world. And more than anything else, what does it mean for reservoir characterization that we have broadened the bandwidth, both on the high-end side and on the low-end side? And what about the source side? Can we do anything there? And it turns out we can. And we'll look at the principles, look at some data examples. And I'll talk about two I think, exciting subjects at the very end. This has been the grand ambition of PGS for, I would say, the last 10 years. And it is really to mitigate the adverse effect of acquiring data the way we do in the marine environment. Because we have sources and receivers quite close to the sea surface. The sea surface is a perfect reflector. So you get the reflection back, we call it a ghost. And what does it do? It creates a very complicated wavelet. And it reduces the usable bandwidth. And we have struggled with these wavelets and doing the econ and trying to recover the data as best as we can. So when we introduced dual sensor technology, which is well known from OBC applications, we remove the reflection on the receiver side. So we create a simpler wavelet. And therefore we broaden the bandwidth, both high and low. When we found a way to remove the ghost and essentially separate the wave field on the source side as well, well, then you have a relatively sharp pulse going into the subsurface. And of course, things happen. But that's what we're interested in. We're interested in the Earth, revealing the Earth. And so we broaden the bandwidth. Of course, we do use air guns and we use hydrophones, so we cannot achieve zero frequency, but we can have the ambition to take it as far as possible. So that's what the story today is all about. On the receiver side, we essentially introduced a dual sensor technology, which is similar to what we have been using on the seabed for a long time. OBC is about dual sensor, and with dual sensor in the time domain, because of the polarity differences between up and down going waves, we can separate it into an up and down going wave. The equivalent in the frequency domain is to say that the velocity sensor and the pressure sensor, the peaks and the notches, they complement each other, and when we combine them, we achieve the broader bandwidth. We become independent of towing depth. We can go deeper where we want to be, where it's more quiet, and then we can also achieve more on the low end side, and as we shall see, this is typically what we've seen over the last 5 years. On the left-hand side, you see a conventional tow at 10 meters, so it's relatively deep conventional tow, versus a dual sensor 25-meter tow, and you can see that there's an abundance of low frequencies, which helps us in the penetration, but there's also more on the high-end side. So this typical picture. Roughly 10 dB down there, around 10 hertz. And of course, now that we towed at 10 meters, the receiver notch is at 75 hertz. And with the dual sensor, we're not restricted by that. But as you can see, we're now restricted by the source notch. So we need to look at that. But that's for later. One of the things that we have seen is that although in a way, we started out from the operations side saying, can we get deeper? Can we record data in a more quiet environment? And of course, then achieve a lot of operational efficiency. We're less weather dependent. That's where we came from. What we have seen is that with the Wave-field separation, which is part of the dual sensor solution. Number one, we get the broader bandwidth. We get a wealth of low frequencies, which allows us to pick better velocities when we're compromised in terms of signal to noise. We can actually, we don't have time to go into that today, but I mean, we can use the up and down going wave field to do a more intelligent SRME, so better multiple attenuation. We can get a better handle on attenuation in the Earth. And it turns out, I'll talk a little bit about that, we can do clever things on the imaging side with the separated wave fields. But taking the broad bandwidth to the, shall we say, attributes like inversions and elastic properties, you will see that the increase in bandwidth, especially on the low end side, has huge implications for the quality and the certainty with which we can derive elastic properties. So, in a way, the broader bandwidth penetrates the entire value chain of seismic. Just a slide to illustrate that this is now becoming, shall we say, industrial. We're in the order of 75,000 square kilometers now of dual sensor acquisition in 3D. So, and we've been through, we've visited most of the geological provinces, I think we can say, around the world. So, starting in Australia, this is Browse Basin. The conventional data, and this is for INPEX, and the conventional data suffered from poor quality, limited bandwidth, poor signal to noise. They decided we need new data. So here you see the time section, and here you see a time slice. On the right-hand side, you see the broadband data, and with the associated time slice. And you may notice that there are interesting three-dimensional patterns there, and we asked ourselves at first, are they real? And the client said when they saw this, yes, it is real. It's a very complicated 3D fracture pattern that you can now derive from broadband data. So we're very, very encouraged by results like this. Moving on to Brazil, this is over the Peregrino field, which was discovered by Anadarko and later on taken over by Statoil. So this was conventional data from 2001, and this is broadband data from 2010. And as you can see there, better penetration, better resolution. The reservoir is up here. And if we look more shallow, it's even more spectacular. So again, I think we're seeing the approach of a new era in terms of seismic data quality. This is an interesting story for me because I'm originally an OBC man, so the story is about the discovery being made by Lundin below the chalk. They had imaging challenges. Those imaging challenges were of a nature that, such a nature that they commissioned an OBC survey. And I'm happy to say, as an OBC man, yes, it did improve the dual sensor, the broader bandwidth, the better geometry and so forth, and it allowed them to better delineate the reservoir. In 2009, we came and we shot a broadband dual sensor survey over the larger field. And I will make, I guess, 2-3 claims. Number one, we compete with OBC quality down at reservoir level. Of course, with OBC, you always have to make compromises because you can only put those cables so close together. So you're always compromised in the more shallow. Here you have the shallow resolution. Price difference, probably a factor of 5 to 10. So I find this interesting. Especially interesting is it also that a stone throw from this discovery is something called Aldous, and then a little bit north of that is Avaldsnes. And no one, I think, thought that we would discover in the order of 2 billion barrels in the central North Sea. So So it's very encouraging for the whole exploration. So, and broadband data will play a vital role, I think, in that new way going forward. The next part of my talk is really about inversion and estimation of elastic properties using broadband data. I'm going to just make two comments up front. When we do inversion, we need to fill the hole at the low end side. We need to use velocities, well informations to fill the gap between where we have good signal to noise in the seismic domain down to 0. Now, with broadband data, we extend the range on the low end side and we extend the range on the high end side. My focus in the next few slides will be primarily to focus on the value of extending data towards the low end side. The second statement I want to make is that it's better to have 0 to 80 Hertz than 10 to 500. And illustrated up here, the side lobes and the interference from surrounding seismic events does limit our ability to accurately predict things like AVO response, for instance. So having a wealth of low frequencies does improve our detailed reservoir description. And that's an important message. So starting out with data from the South Viking Graben, this is typical of what you up till 2009 could get in terms of seismic from the area. From 2009, we have started reshooting almost half the central area of the North Sea, the south central area of the North Sea, 25,000 square almost, with broadband data. And what kind of improvement do we see? Well, immediately you see the improvement in low frequencies, better penetration, better delineation of structures, but you also see shall we say, the improved resolution. So one thing is shall we say, the quality of the seismic. So that's good. And in terms of trying to quantify that, it's in the order of something on the low end side and something on the high end side. And said, let's put it in log scale and look at the low end side. Conservatively speaking, we move from, say, 10 Hertz down to, say, 5. So that's an octave. That's the equivalent of going from 25 Hertz to 50 Hertz, actually. So it is very substantial. And I mentioned, yes, we see the improvement in the pure image. But what I'll concentrate on now is to look at an inversion and see what it means to include that bandwidth, that extra bandwidth in the inversion. So we had access to 3 wells, dipole and sonic. We used velocities to create an acoustic background model. And then, so on the top you see the model with the 3 wells used as constraints. We then did a blind test. We took out the middle well. And then we did this exercise for conventional bandwidth and for the extended bandwidth. And here you see the results. On the top, you see the conventional bandwidth from 10, so live seismic data essentially from 10 Hertz up. And then you see the well and reasonably good agreement there. So this is P impedance. Reasonably good agreement there, but that's no surprise because we use them as constraints. In the middle, not so good. At the bottom, you see broadband data. So live seismic data from 5 Hertz up. good, even better agreement, I would claim. Reasonably good agreement, much better agreement. And let's look at the details. So this is P and S impedance, and we have, of course, now the dipole and the sonic from the well, so we can integrate them. And on the left-hand side, you see the difference between the curve, which is the integrated log data, compared to the inverted PNS. For conventional bandwidth, here you have the broad bandwidth. Live seismic data down to 5 Hertz. Much better agreement. Of course, we used exactly the same data now. So we just this is a pure bandwidth comparison. So what is the message? The message is that with those 5 extra Hertz on the low end side, we can extrapolate elastic properties away from the well with greater accuracy and greater confidence. Very far from, shall we say, the operational perspective that we had by towing deeper and all that. The real value in broadband data is there for you as end users. Now, how accurately can we estimate an impedance profile? Well, we have taken the broadband data and we have compared it to a nearby. So this is a nearby well, close to where you just saw data, and we've filtered the log data down to the seismic bandwidth, and we compared the purely seismically derived impedance trend, and I'm pleased to see that we can actually, independent of well log data, get that close. That is, shall we say, holds a lot of hope for us in terms of being able to do quantitative interpretation based on pure seismic. This is an AVO case study. It's from Northwest Shelf of Australia. It's a gas field with 2 producing sands. We had conventional data and we had broadband data. And you can argue that, well, we have a bit better resolution. We can see the 2 reservoir units a bit better. The seismic, though, is not day and night. And that's actually my point here. It's not day and night, but let's look at derivatives. Let's look at attributes. In particular, let's look at AVO. And so we had access to a well, and what you see there is, if we plot acoustic impedance against VPBS, the gas sands, they stand out there with a VPBS in the order of 195 or so. Now let's do an AVO inversion with seismic data. On the left-hand side, you see the conventional data. On the right-hand side, you see the same exercise done with broadband data. Now, in the acoustic impedance domain, the range is roughly the same. No big surprise. That should be frequency independent. In the VPBS domain, we see much more, shall we say, less precise estimate for the reservoir sands. We're right there with 1.95 with the broadband data. The conventional data is much more smeared out. What is this? It's about those side lobes. And it is the broadband data, and it's especially the low-end side, that helps us, because the reservoir interval is better isolated with broadband data. So you have less interference from surrounding events, and therefore you can do a more accurate estimate of, in this case, VPBS for the gas sands. Now, with all these good things said about broadband data, and so far we've only looked at the effect of the receiver side improvement. All the more a good reason to look at the source side and see if we can achieve that extra lift, that further lift in the bandwidth. So So I'm going to talk about something that we have come to call Geosource. It used to be a company. it's not registered anymore. Geosource is about two things. It's about having a vertically separated source, and that's relatively easy to achieve. You could fire your sources in such a way that you always have two source points on top of each other. If you do that, you can separate the wave field, essentially. Same thing as if you have a receiver separation. But if you did this in a conventional way, you would lose half the fold, because you could only fire those sources so often. So Geosource is about having a vertical separation, but firing them almost at the same time. But we fire them in a randomized way, and that allows us to separate the two sources and put them back together again. That's what it's all about. A time-distributed source, a depth-distributed source. We can separate it, and we can deghost it, basically. So if you look in the shot domain, you will see that the deeper array fires first, and then comes the shallow array and fires a little bit later within a certain time window. But if you look at now for a common channel for different shots, of course the second source will fire at different times. So we now have a situation where one is random, but we know all these delays. These are not random, but they are pseudo-random, so we know them, so we can actually align on that energy as well. And by doing that, we will see that the other contribution is random. And that we now know that we have powerful techniques in our geophysical toolbox to separate what is continuous and what is random. And that is essentially how you do the source separation. So these are shot profiles. As you can see, they are now contaminated. We see the deep source goes off, and then the shallow source, and at a slightly different time. And of course, it's all over the place. Now we can do deghosting, and using the overall over-under principle. And we see that a lot of the source separation is actually achieved through the deghosting. There's a very simple reason for that. When you look at posthumous least square solution, you will find that by deghosting, you actually do quite a bit of source separation. But then we can clean up and we get a nice clean gather. So so how much contamination is left? Well, it's easy to check because we don't have to shoot this. We can actually do this on our computer and we can get the perfect answer. And the answer is you can get below 1 dB. So you can do almost a perfect separation. And actually the ghost removal process itself helps us, does actually 60-70% of the job. So let's look at data. This is conventional source at 7 meters, conventional spread at 8 meters. So conventional. This is GeoStreamer. This is the what we have been looking at so far. This is the GeoStreamer Geosource. Step back. So conventional, GeoStreamer. So dual sensor on the receiver side. Ghost free. Look at some pictures afterwards. But I find these two images and the comparison quite interesting, because on this side you have the same spread, you have the same source essentially. It's 3,600 cubic inch, fired at 2,000 psi. It's hydrophone at 8 meters. The same processing sequence. Here you have 3,600 psi, 3,600 cubic inch at 2,000 psi, dual sensor. It's exactly the same hardware that has acquired these two images, or generated those two images. This is more intelligent seismic. And we are moving there. Now, we're not limited to just 3 arrays. We could introduce 4, and we can tow them a bit deeper. And we have done that. And then you get a further uplift, because you, by towing the source even deeper, you get even more lift on the low end side. And you're not sacrificing any of the high frequencies. So this is conventional. This is geostreamer geos. And put it in short, I think we are entering a new era in seismic. It is about the high-end side, but it also is a lot about the low-end side. So in this case, basalt, top Paleocene. So as you can see, it's not that shallow, and we preserve fairly broad bandwidth, fairly deep into our data. So again, legacy data versus broadband. I'm very pleased to show these examples, because that extra lift that we've seen. I mean, I had been talking to you about dual sensor and all the benefits. Just imagine we start doing reservoir characterization with this kind of data quality. Conventional, I'm sorry. Oops. There you go. It's almost like we don't have to invert anymore. It looks almost inverted. You see the geobodies. And this kind of data is much easier to interpret. It's good for the eye, it's good for the auto tracker, it's good for those kind of simple things as well. And I think it is a lot about the lift on the low end side. And look there from 10 hertz down. We have seen, and in this particular data set, we have good data at 2 hertz, which means we can do full waveform inversion, and we can create velocity models straight from data. We've just started to scratch the surface, I think. So, what else can we do? Well, when we've separated the wave field, we can do things. Now, historically, of course, seismic has been about primary energy from the source down to an impedance contrast and back to the receiver. And our imaging software is designed to derive velocities and image that point. What about things like this? Well, we could find ways to, what we do have, we have very powerful tools to take it away. That energy that goes up there and bounces in the water layer. And it's called multiple attenuation. Instead, we could potentially image that energy. Now, it's not straightforward. Issues with imaging conditions, there are issues with crosstalk, and so it's not straightforward. But if you have separated wave fields, you have a great advantage. So this is just to allude to the fact that if you have only primaries, your cone of imaging is more narrow. If you look at this as a source point, generally speaking, and if you take into account now all the receivers, your aperture changes. So you can do the imaging. And this is the C model. So this is primaries, and this is with multiples. This is imaging with multiples through the C model, and this is a depth slice. And there are differences, simply because of the difference in aperture. But look at some of the footprint that you see there. You don't find it there. And the reason for that? Well, you have a source there. You have a different aperture. And we can rethink our whole acquisition strategy, because now we have sources all over the place. In principle, we have sources everywhere we have receivers. So this, if we can make this happen, it can also not just give us an uplift on the receiver, on the imaging side, but it would also mean that we can rethink our acquisition strategy. So maybe we have something that is better than we think, actually. And this is real data. I mean, we'll at the Copenhagen conference, we'll show you some more exciting data. So what you see there is primaries, and over there you see multiples. So I had a few other slides, but I think I'm gonna leave it there and say that with the improved bandwidth, we see that, and the wave-field separation associated with it, we see that we are approaching a new era where we can do new things and do things with greater confidence, and I think also use seismic data in a quantitative sense that hasn't been possible up till now. So with that, I would say thank you very much, and open up for questions.
Okay, time for one or two questions, if anybody has any. Yeah, please, in the middle there. Be good if you say who you are and where you're from. Thanks.
Hey Ed. Dave Forecast from Cairn Energy. Just a quick question about the Geosource specifically. How does the source's signature get derived? Is it through nucleus, like your conventional source of PGS?
It's a combination of modeling and near-field measurements. We see the need to improve the quality of the near-field measurements, because we need to calibrate those sources. As you approach 0 hertz, numerical modeling is non-trivial. So you need a calibration there. And especially when you go deep, the 10-14 combination needed that near-field calibration to get it right.
Okay, anybody else? Yeah, please.
Ed Tree, independent consultant. Eivind, you've done a fantastic job of expanding the spectrum. In fact, you have essentially a white spectrum for the acquisition system, but the Earth itself attenuates the higher frequencies. Traditionally we used to tow shallow to boost the higher frequencies by a factor of 4. Have you thought of extending this concept so that you can actually shape the outgoing spectrum, or the total spectrum of your acquisition system, to boost the higher frequencies and therefore get a flat spectrum with the received seismic signal? Just like you do with nonlinear vibrosize.
It's a very interesting thought, and what I have shown you on the source side is, of course, just one, we said two points on top of each other, basically. You could potentially envisage more than 2 levels. 3, we have done some preliminary tests with 3, and then it's a question of how do you fire them. And there could be randomization schemes that would effectively do the same for you as you do on your vibrosize by sort of shifting the energy towards the high-end side. So an interesting thought, but we need to preserve the low-end side.
Yeah, of course, most important.
Okay, anybody else? Ian, you're looking mildly quizzical.
Well, it was going to be a response to Ed Tree rather than to Eivind. Thank you, Eivind. Wonderful, wonderful paper. But just to respond to Ed there, I mean, I would have thought that the Earth eats up the high frequencies so drastically that the great difficulty, even you have to go to great lengths just to get an extra couple of hertz, 5 hertz, something at the top end of the spectrum, whereas, as Eivind says, it's much easier actually at the bottom end.
Yeah, I agree in terms of the way that
for that, Eivind. Thank you
Thank
very
you.
much.